Welcome to part 5 of the Digital Dynamics Studio walkthrough tutorial. Today we're going to talk about visualization, how we can use the tools of Digital Dynamics to visualize the flow in a very meaningful and effective way to see what the results look like, what happened in the simulation. So if you remember from part 4, we ran the simulation. We talked about loading a model and setting up the simulation parameters and running the simulation. So that's kind of where we're at now. You can go back to that tutorial and review it if you want, but we're starting out here. We have 2,000 simulation frames computed, as you can see here from the timeline, and we have the default visualization parameters here shown on the screen. So as mentioned last time, all the display parameters which you're seeing on the screen is controlled by the display parameters that you can open up here on the upper right. And before we go further, we want to note from last time, if you remember, this tutorial recording software isn't doing a very good job of recording the animations as we play them back within the studio. On my screen, it's moving very smoothly, very, natural, very fluid motion, hunting every frame. But probably in the tutorial, you're seeing a very jerky animation. It just can't keep up with the updates that the Digital Dynamics Studio is doing. So because of that, from time to time throughout this tutorial, we'll be inserting video clips of what the simulation results will most likely look like to you on the screen if you were performing this tutorial on your own, seeing the full motion of the results. Like I said, the tutorial itself, the tutorial recording software isn't doing a good job of recording all of the frames that we're seeing here on the screen. So we'll be inserting videos from time to time to show you exactly what you would most likely see on your screen if you follow along the tutorial. Okay, so in the display parameters, you can see by default we're seeing the mesh and velocity vectors. And that's exactly what we're seeing on the screen. The mesh is self-evident. It's the unstructured mesh that is used as part of the backbone of the simulation. We have our elements, the triangles, and the nodes, which are the corners of the triangles. And if you remember what the simulation engine does, it solves for the fluid flow variables from the Navier-Stokes-Schrödinger equations at each of the nodes in the mesh. And in this case, it's velocity vectors. There's two components, an x and a y component of velocity and pressure at each of the nodes in the mesh. With different formulation types, you might have some other variables like temperature, some other things, but in this formulation, we have velocity and pressure computed at each of the nodes in the mesh. And you can see the structure of the mesh to maintain accuracy. It put more nodes and elements in regions where it needs them, where the solution is changing rapidly, or there's more variability in the results at those locations. So that's the mesh. Is very self-evident and straightforward. And you can enable these by just pushing the eye icons. The mesh and velocity you can enable at any time. We'll talk about these other variables in a moment, but these can just be turned on or off at any time. The next one is velocity vectors, and we briefly mentioned this at the last part 4 tutorial. But these show the direction and magnitude of the fluid velocity at each node of the mesh. You can see the direction is indicated by the vector, and the length of the vector corresponds to the speed of the flow at those locations. You can see down here, the length of the vectors is much lower than out here, which means that the speed of the flow is much slower in those locations. But in all cases, it shows the direction of the flow at each of those locations. It gives a very good overall picture of the flow by just watching the velocity vectors alone. There's a scale parameter here, and anytime you can increase or decrease the overall length of the velocity vectors. Sometimes they get too long and you just can't really see a good picture of the flow, and sometimes they're too short. And again, you can't see a good picture of the overall flow. So usually there's a sweet spot somewhere in the middle where you get a good length of the vectors and you can get a good picture of the motion of the fluid. So you can either use these arrow buttons up and down to increase or decrease the size of the vectors, or just type in a value directly in here. But usually we use the buttons to scale up or down the vectors in total. So you can see here when I play back the animation, just by looking at the velocity vectors alone, you can get a good overall picture of the fluid dynamics and what's happening in these results. You can see that the flow encounters a cylinder on the left and kind of splits into two parts. One half of it goes above the cylinder and half of it goes below the cylinder. And you can see behind the cylinder, a wake develops. There's lots of little vortices that are formed, and then it's called vortex shedding. And they're formed behind the cylinder, and then they're kind of detached from the cylinder, and they move downstream. So you can definitely see that happening right here. This is called vortex shedding. It's a very famous, very well-known phenomena that happens behind most objects, actually, when there's fluid flow going around. Most objects, a square, cylinder, a wing, lots of different things. This is a very common feature of the flow. And you can see these vortices are shed from behind the cylinder and then are kind of carried with the flow, advected downstream until, in this case, they exit the domain here on the right. It's a very well-known phenomena. So that's velocity. And again, you can enable that by these eye icons here on the left at any time, or use them in combination. The next category are these scalar variables. Those are not vectors, they're single value variables, pressure, vorticity, and speed. And again, if there is a different formulation, there might be others here like temperature. And we'll talk about those in a moment. It's another thing you can look at. The third category here are particle traces. That's a different technique for visualizing the fluid flow results. And again, we'll talk about those in a moment. But first I want to talk about these additional dialogues that can be enabled here in the lower part of the display. First, let's talk about the console. You can bring that up here. This just is a console. It provides text output from the solver itself, and periodically it prints things to the screen that a user might want to know about. You know, the model had 16 points and 8 curves, and the initial mesh had 290 nodes and 464 elements. Just some textual information. Usually there's not anything super relevant there. We don't really look at this too often. I just want to highlight this icon here, which is disabled. This is the benchmarking tool, would be popped up if you push that. You can only run the benchmarking tool if the simulation hasn't been computed yet, so that's why it's disabled right now. But you can read the documentation about this benchmarking tool. It's a good way to benchmark the performance of your system. You know, every system is going to be a little bit different, and this is a benchmark tool. A good way, it runs a quick simulation in the background and tells you the performance of the simulation, so it's a good way to measure the performance and compare with other computers the performance. But you can look at the documentation about that, but that is access to the console right here. So we can close that by pushing the X icon here. And let's talk about the next item. The time curves dialog here is much more interesting. Let's bring that up. So this is the window in the lower right, and it shows scalar variables, single values that change over time. And I can play the animation here, and you can see how the time curves change with respect to time. The current frame is always highlighted here on the right of the curve, and if you look closely, the current frame, which is highlighted, is 1775, and it shows the values of these curves at that value. So there's 3 different types. These are toggles up here on the top. There's 3 different types. Force curves, performance curves, and convergence. And we'll talk about each of those next. So the force curves is the most important one. During the simulation, along with these fluid flow variables that we're seeing here, there are forces generated by the fluid on each of the boundaries of our simulation. Remember, boundary 1 is the cylinder, and the fluid is imposing forces on that boundary, and force is a vector, so there's a force in the x direction and a force in the y direction. And that's what this is plotting, is the forces that the fluid is imposing on the boundary at each frame on boundary 1. By default, it shows the forces on boundary 1 in the x and the y direction. The blue curve is the force on boundary 1 in the x direction, and red is the force on boundary 1 in the y direction. And this x direction, that's the drag, the fluid drag imposed on the cylinder. So that's blue is the fluid drag, and the force in the y direction, that's the side force, that's the lift. And it's perpendicular to the direction of the flow, so that's the lift. So that's red. Red is showing the lift. Let me pause that here. Let me jump to the end. So red is lift, and blue is drag. So you can see that the drag on the cylinder is around 1.56, and the lift oscillates up and down around 0. There's no net lift on the cylinder. It's a cylinder symmetric, so you would not expect there to be lift on the overall lift on the cylinder, but instantaneously, due to the vortex jetting behavior, lift is going up and down throughout the simulation. So that's a very common, very typical result for these kinds of flows. As we said, by default, it shows the forces in the x and y directions for boundary number 1, but that can be configured through this gear icon right here. It brings up this dialog, which you can look at the manual, the documentation for more information about these, but you can change it. This is the force in the x direction on boundary number 2, and so forth. So you can change what's shown in the screen by using this dialog here, or you can change the color of the curves if you want to through this dialog. Let's go back to blue. But you can read the documentation for more information about how to configure the force curve. The next one here is the performance curve, and it shows the various things about the performance of the simulation over time. The blue curve is let me pause it here for a second. There we go. The blue curve is the size of the mesh as measured in number of elements, number of triangles, over time. You can see that it starts out fairly low in size and reaches a certain size of maybe around 4,000, 5,000 elements. But then when the vortex shedding happens, the mesh increases further to a little under 10,000 elements and kind of maintains that value throughout the rest of the simulation. That's because if you look at the simulation parameters, in the advanced parameters, there's this thing called max mesh size limit, which is set to 1, and that corresponds to 10,000 elements. So the solver is not going to let the mesh get larger than 10,000 elements with that value. We could have changed that to 2.0 and rewritten the simulation, and then this mesh size would probably go larger. It might not reach exactly 20,000 elements, but it would definitely probably grow larger than being capped at this 10,000 elements. So that's one way to control the size of the mesh during a simulation is this max mesh size limit. But 1 is a good default, corresponds to 10,000 elements, and that's why the simulation is capped at that value. And this red curve here is the speed of the simulation over time. So at this point, this frame, what is that, 821, this solver was computing about 62 frames per second, which is actually pretty high. It was doing a really good job. You can play that here and see how the speed performance of the solver changes over time for various reasons. There's all kinds of reasons. It's a fairly complicated solver. But that's the red curve here, is the performance, the speed of the solver at each, roughly, average speed of the solver at each frame throughout the simulation. And these are actually pretty high numbers. I would consider real-time simulation to be anything at or above 30 frames per second. And for this simulation, we're well above that. In theory, we could have changed the max mesh size limit to, say, 2, which corresponds to 20,000 elements, and let the mesh grow larger, a more detailed, more complex simulation. And then, of course, it would have ran slower, but in this situation, it probably still would have ran what we would consider real time. The next time curve type is the convergence plot, which you see here. And this is a more advanced technique. It's just a way to monitor your simulation, make sure that it's working properly. If you go to the documentation in the governing equations section, you will see that the Navier-Stokes equations that we're solving are nonlinear. So you have to break it out, the solve at each time step at each frame into sub-steps, sub-iterations, nonlinear iterations. That's kind of what you're seeing here, the residual of the formulation at each nonlinear iteration for each frame. So the spikes themselves are the frames, but in the dots between are the nonlinear iterations. So what we're measuring here is the residual of the formulation. It's really almost the remainder of the solver, the remainder of the formulation. It's not specifically error in the results. That has more to do with the mesh density and the quality of the mesh and the refinement of the mesh. You can kind of consider it the remainder of the formulation. Definitely you want to be close to 0. 0 is the ideal, but you can see at each time step, the solver is pushing that residual to a much smaller value at each frame. So this is typically what you want to see when you run a simulation. It's not always going to look like this, but this is generally what you want to see. But this is an advanced topic, so we're not going to really go into detail about that here. Force curves themselves are much more interesting to follow along. If you're interested in the forces that are generated on the objects, the force curve is much more interesting. So you can close that out here by pushing X at any time. Let's go back to the display parameters. Next, we want to talk about these scalar variables. Let's turn off the vectors and let's look at pressure. There we go. So here's a scalar variable of pressure, and the way this works is that there's always a color map associated with each of the scalar variables. And there's some default color maps, but you could choose the color map through this menu here on the right. We're not going to talk too much about this. You can look at the documentation. But this is the color map here for pressure. It's the rainbow color map. Smaller values are blue, then they go to a kind of a light blue, a green, a yellow, and a red. So what happens is this min value of pressure, in this case minus 0.5, gets mapped to the blue value here on the left of the color map. The maximum pressure of 1.0 here gets mapped to the right value of the color map, which in this case is red. And everything in between minus 0.5 and 1 in pressure in the domain gets mapped to some other color between those two values. And you can see that here. So the blues are the low pressures and the reds are the higher pressures. But one thing that plays an important role in this kind of visualization are the min and the max values themselves. Right now, I don't know what the min and the max values of pressure are at this particular time step. Minus 0.5 and 1 are good guesstimates, but I don't know what they are. And you can change these at any time, and you can see how the colors themselves change because we're changing the mapping of pressure values to colors in this case. But a quick way to set these values is by pushing the auto button. When you push the auto button, it'll actually look at the pressures at this particular frame. What is the maximum? What is the minimum value of pressure at this particular frame? It'll calculate that and put those values here for min and the max. So when they do that, you can see that the smallest pressure everywhere in the domain at this particular frame is minus 1.11, and the maximum pressure is 0.6. And it uses those values in the mapping of colors to pressure in this case. So it's a little bit a better picture of the flow. By pushing the auto button, it fills in those values automatically for you. When you play it back, you can see what pressure looks like during the simulation. Sometimes we look at pressure. It's a very important variable in these results. But it's not, as you can see here, it's not super intuitive. It doesn't really give you a great picture about what's happening in the flow. It's definitely important, but we often don't look at pressure. It's not that informative about what's going on in the results. The next scalar variable to highlight is speed. There we go. That's the magnitude of the velocity vectors at each location in the domain. And again, if you look at the color map, it's using the same rainbow color map. The pressure was small. Lower speeds are highlighted in blue, and higher speeds are highlighted in red, with the default min and max of 0 and 1. And again, I can push the auto button to fill those in with the actual minimum and the maximum in the domain. The minimum is still 0, of course. The velocity on the cylinder is 0, so that's not going to change. But you can see here that the maximum velocity in the domain is 1.6 in these red regions out here. So you can see that, so basically this means that the fluid is accelerating as it goes around the cylinder. Half of it goes one way, half of the fluid goes the other way around the cylinder. And it accelerates around the cylinder because of the incompressibility constraint. So you can see that it increases in velocity as it goes around the cylinder in these red zones. And you can play that back, and you can see it's a very complex flow. There's a lot going on here, but again, it's not super intuitive. It's not really doing a great job of showing you intuitively what's happened in the fluid flow results. So we look at speed sometimes, but not a lot when we're analyzing these results. And normally we look at vorticity, which we'll talk about next. So we can enable vorticity instead. Oh, I should quick mention first that you can only have one of these scalar variables on at a particular time. As you can imagine with this type of color display, you can't show two at the same time. You can only show one. So these are radio switches that only allow you to have one on at a time. Anyway, back to vorticity. So vorticity, if we play that back, is a much more intuitive variable to look at. It gives a good overall picture of the fluid flow results. As you can see here, the vortex jetting behavior is clearly visible as these vortices are formed behind the cylinder and then detach and move downstream. Vorticity itself is not solved for in the governing equations. We did not solve for vorticity. It's a derived variable. It's calculated from velocity vectors. Vorticity is defined as the spatial gradient operator crossed with the velocity vector, and it creates a vorticity, which in 2 dimensions, vorticity can be considered a scalar. Red, as we see here, these red colors are basically the turning of the fluid in the positive direction. If you use the right-hand rule, red is turning of the fluid in the positive direction, and blue is the turning of the fluid in the negative direction. So we can turn on the velocity vectors and look closely. You can see, let's pause it here for a second. You can definitely see that the vectors are curling in the positive direction using the right-hand rule. So they have a high red positive vorticity region, whereas in the blue areas, it's the curling on the fluid in the negative direction using the right-hand rule. So they get assigned a very negative vorticity value if you play that back. So definitely you can see the correspondence between the velocity vectors and vorticity. Again, that's because the vorticity themselves was not computed directly. It's derived from velocity as the spatial gradient crossed with the velocity vector. So oftentimes we look at vorticity when we're analyzing these kinds of 2-dimensional results. It does a great job of kind of giving an overall picture of the flow, as you can see here. And again, we like to sometimes mix it with, the mesh, combine these two, or velocity itself. When they're combined, let's turn off the mesh. When they're combined, they actually give a very good overall picture of what's happening in these fluid flow results, as you can see here. So let's turn these off. Let's talk about the last category of visualization, the particle traces. Let's turn on irregular particle traces. So this is a very different technique for visualizing the fluid flow results. Basically, when you're using, let me turn that on. When you're using this technique, what happens is, just for visualization, we release hundreds or even thousands of particles, massless particles, into the flow that get carried with the fluid, as if you can think of it as like particles of dust or something very light, like dust released into the fluid, and it just gets carried with the fluid. And because of their motion, you can get an overall picture of the fluid flow results, as you can see here. Oftentimes, these are good to combine with vorticity to give you even a more enhanced view of the results. But it's a very intuitive technique to visualize the results. Again, these particles are not calculated or used in the solver at all. They're just here for visualization. So a couple parameters associated with them. Density is basically the overall density of the fluid. Let me pause it here for a second. So density of 1 is the default. You can see as we increase density, the overall density of the particles become higher. Energy, you can see here that the particles are a little more dense where things are happening. That's called the energy in the fluid. So we actually see more particles in those areas where there's higher energy. If you turn it off by setting that value to 0, you can see that it's a uniform distribution. It's harder to see what's happening in the detailed regions. So usually we like to have some energy so we can kind of see the details a little bit better. This white noise, I can change it here. It just gives a different distribution of particles in the domain. You can see here with blue noise, it's a little bit more regular distribution, a little bit more pleasing distribution. But it's more, computationally, it's more expensive to compute this distribution. So we use it sometimes when we're making an MPEG movie or something to export. But if you're just interactively displaying something, usually the white noise is better, since it's a simpler algorithm and will be calculated much quicker than the blue noise algorithm. So that's the regular particles, and next we'll talk about the irregular particles. Next we'll talk about the regular particles. So when we switch to regular particles and play the animation, let me turn this off. Here you can see that it's different. It's more like streamlines. If you're familiar with streamlines, we release a set of particles along inflow boundary. In this case, 11. The number is 11. So if you count them, there's a stream of 11 particles released from the inflow boundary, and they get carried downstream, go around the cylinder and in the wake. And again, it is a great way to look at the fluid flow results, a very intuitive picture of what's happening in the fluid. Usually I like to increase from the particle density to something a little bit higher, so you can do that there. And another thing you might change, you can see that the width of this region is by default 1.0, where the particles are released, right there. And If I want a little bit tighter stream of particles, I can decrease this to 0.5 or something. And then you pause it here. You can see that the stream of the particles is a little bit denser. Gives a more detailed picture of the results. That's the width. And you can increase it, something large if you want. But usually, a nice tight stream of particles that go around the object and give you a good picture of what the fluid flow looks like. Again, we like to calculate added vorticity with that sometimes. And again, a very intuitive, very detailed picture of the fluid flow results when you combine regular particles with vorticity. And the last thing I want to mention here is just the interval. 1 means a releasing set of particles at each frame into the fluid. For example, if I change it to 10, you can see that here we get waves of particles. Only every 10th frame are we releasing a set of particles into the flow. So it's a different kind of visualization. Sometimes you want to increase the width to something larger. When you're releasing waves of particles, then you increase the density, 51. So it's a different way to visualize the results, as you can see here. You can create different effects and different ways of looking at the flow. So that's it. Quickly for the display, you have a bunch of options that you can enable and disable at any time and combine them however you want. Lots of different options, lots of different ways of looking at the flow. And like we talked about, these other 2 dialogues, which you can use to show forces and various values over time that are changing. So that's it. One final thing you might want to do is use the movie button to record an MPEG movie of your simulation that you can download to share with others or use in a presentation. And that's the topic of the next tutorial, part 6, movie making. So go there and learn that topic, and we'll see you there. Thank you.